Good morning, everyone, and welcome to DP and Applied Mathematics seminar. It's a pleasure for me to open 103 of this seminar. Today we have two excellent speakers, Sergey Sergeev and Livio Ignat. Introducing Sergey Sergeev, we have the Professor Anna Dubova. Thank you, Anna. You can start, please.
Okay, thank you very much, Juan, for the introduction. So it is a pleasure for me to introduce Sergey Sergeev. Is my colleague we studied at the same university. So he finished his PhD in Moscow State University, and he worked in the Russian Academy of Science in the Institute for Problem in Mechanics. And for 2 years, he is working now in Pontificia Universidad Católica from Rio de Janeiro. He is a specialist in the asymptotic semiclassical analysis in the question of the wave propagation. His interest lies in the question of propagation of linear dispersive waves. In particular, he is interested in the homogenization procedure for the localized waves, which leads to the appearance of the dispersion effects. So today he will give a talk entitled Semiclassical Homogenization in the Problem of Localized Linear Wave Propagation. So thank you very much, Sergey, and you can start.
Thank you, Professor Anna. I would like to thank organizers, Professor Joan, Professor Anna, for a kind invitation to give a talk here. So, as mentioned, I'm interested in the case of dispersion effects, which appears during the wave propagation, localized wave propagation. So, I would like to share some of my knowledge with you, and so the plan of my talk is the following. So I would like to state the problem which I want to discuss, and then I want to give some example in one-dimensional case, and mostly I will discuss generally this example, how how dispersion effects appears in this example. Then I will discuss this dispersion effects, make some statements, analysis, and finally I will come back to the initial problem. So for the general case, and how we can, by analogy, try to bring some analogy for the general case with this example. So how we can deal with these problems. So let's go to the problem description. So we consider the following wave equation with fast oscillating velocity c square, which depends on two variables, two arguments, theta x over epsilon and x. So delta is the Laplacian, x in the n-dimensional vector. We consider it in the whole space, and vector function theta capital of x is the vector function of theta 1x and etc. theta m of x. M is numbers of this function theta is less than equal than dimension of our space, which we call this function theta k oscillation phases, and we assume that they are smooth and the gradients of these functions are linearly independent for all x in our space. And parameter epsilon describes is a small parameter which describes the fast oscillations. And as for the function c, which is coefficient, we assume that this function is strictly positive and bounded, so between two positive constants, m small and m capital, and we also assume that this function c of yx as the function of first argument y is 2 pi periodic with respect to each variable yj. So about theta function, Yes, the form of the oscillations which we want to discuss is the form of the theta of x over epsilon. And this fast oscillations is described by this theta function, vector function. So traditionally, you can recall that traditionally, the fast oscillations are described in case where x over epsilon, so in case where theta of x is function of x. In our case, we can describe more complicated form of fast oscillation. So here I want to present some example of possible function of c square. So for example, we can consider 2 plus exponential minus x squared times cosine x2 over 0.1. So in that case, we have this oscillations, some periodic structure with respect to the variable x2, but we can consider different situation, different form of the oscillations, when we, instead of x2 in this inside of the cosine, we insert function theta of x, which is x1 squared plus x2. And in this case, the fast oscillations of the coefficients are much complicated. So this approach allows us to consider more complicated form of the oscillations in the coefficients. So we want to consider the Cauchy problem, and we pose the initial localized conditions. So we have the initial perturbation v of x over mu, and initial velocity is 0. So here appears another parameter, mu, is the localization parameter. And further, it will play the role of the wave length of our wave propagating waves of the solution of our wave equation. And we assume that function v of xi as the argument of xi is the smooth fast decaying functions on infinity with all its derivatives. So for example, we can think as it is in the Schwarz space, for example. So this is our Cauchy problem for our wave equation, for our localized initial conditions, and we want to describe the asymptotic solution of this problem when mu, our small parameter localization, goes to 0. The main difficulty here is the presence of two small parameters, epsilon and mu. Generally, during this talk, I will assume that we have this following relation that epsilon over mu is less than 1. So here I want to make some comments. So we will discuss the idea that we have the asymptotic solution when mu goes to 0, but during our applications, mu and epsilon are some numbers, some small numbers. So, for example, as the Planck constant in quantum mechanics is the small parameter, but it's fixed number. So the idea is that what can we do with these small but fixed parameters, and how the asymptotics when mu goes to 0 can be approximate our solution. So we have two sub-problems in this statement of our problem. The first sub-problem, this is a big problem of the homogenization. There are a lot of works about homogenization. So here I presented several names, Ben-Susan, Leons, Papanikolaou, Alere Pyatnitsky, Sionarescu, Brassar, Sanchez-Palencia, and also Aleynik, Zhikov, Kozlov, Bakhvalov, Panasenko. There are a lot of works about homogenization. But the case is that we have the initial condition of the special form, which is localized. Therefore, we can say that this function is fast changing. So we have to take into account this property of our solution, and this can be done with the help of the operator approach, and called adiabatic approximation in the operator form, or operator separation of variables. This is also quite known field of study. So here I mentioned some my colleagues, Доброхотов, Nazaykinsky, Tirotsy, Grushin, Bruning, and also a lot of other. So here I mentioned this chapter in this book by Dobrokhotov and Nazaykinsky about homogenization and the Cauchy problem for the wave equation with rapidly varying coefficients. So now this is the first problem. The second sub-problem which appears here and which we want to take into account is the asymptotics. We want to construct the asymptotic solution. So, and we want to present it in some analytical form. And this can be done by the semiclassical approach based on the Maslow's canonical operator for the localized initial conditions. So again, this is quite known field, mathematics. So I also mentioned Maslow, Fedoruk, Dobrokhotov, Nazaykinsky, Shafarevich, Tolchenikov, Anikin, Minenkov, Tirotsy, Zhivadov, and many others. And this approach gives us some function which satisfies for the equation with some small residue. So here again, I want to mention several papers, couple papers. So this book by Maslow and Fedoruk, Semiclassical Approximation, this classical book, and quite recent book by Dobrokhotov, Nazaykinsky, and Shafarevich about the localization, localized asymptotics. So what we want to discuss in this present talk is that we want to discuss the homogenization part of this problem. So we are interested in the special case of the initial data which are localized. So it gives us some sort of multi-scale problem with two small parameters. And the question what we want to discuss here, the answer for the question is how the localization affects to the homogenized equation. So what we obtain when we want to when we need to take into account the localization. Again, we will not discuss here the questions of the existing solution and the functional spaces, as it's completely different and very difficult questions. So we take into account that we want to construct some asymptotic solution. So this talk mainly based on this paper. So now let's consider the example. Yeah, so let's start from the example, which I hope gives the idea of what we want to do. So let's consider one-dimensional wave equation with coefficients when it depends only of x or epsilon. So quite similar dependence, but we have the localized initial condition and function c of y is periodic. Now, we are looking for our solution in the form of the function phi, which is a function where we separate small, slow variable x and the fast variable x over epsilon. It also depends on the small parameters, epsilon and we assume that function phi is our new unknown function and it is periodic with respect to the variable of y with the second argument. So substitution of this form of our solution to our wave equation gives us this new equation for the function phi. And it is very interesting that this equation is equation with the constant coefficients with respect to the variable x. And therefore, we can do the Fourier transform for this in this equation with respect to the variable x. Okay. So the problem here with Fourier transform that we need to adjust it to our localization function. So we introduce some f mu Fourier transform with small parameter here, here, and here, and as well as the inverse Fourier transform when we want to obtain the localized function. And the thing is that it is known that the operator of derivative is after the Fourier transform gives us the multiplication by a variable p. And in our case, because of localization parameters, this operator is not z over dx, but mu d over dx minus I mu d over dx gives us multiplication by variable p after Fourier transform. So let us multiply our equation for the function phi to the minus mu square. We obtain this equation, and after Fourier transform, we will get the equation for the Fourier transform of function phi tilde. So it is the equation with respect to the, so here we have the operator with respect to the variable y, and p is some sort of the parameter. So what we want to do here is we want to look for this function phi as the product of two functions, phi, which depends on the variable y and p, and some function with tilde, which depends on p and t. In addition, we assume that this function v tilde is the form of this exponential, where a amplitude is some function which can be determined from the initial conditions, and omega is some sort of frequency. So as you can see, here we separated our first variable y into the function phi. So substitution of this form gives us the spectral problem for the function phi. Yes, so here is operator. Here's our operator. This is differential operator, second order differential operator. P is the parameter, and omega square, our frequency, is now the eigenfunction, which also depends on the parameter P. So how we will solve this problem? We will solve this problem in the form of power series. Recall that we have epsilon over mu is the small parameter, and therefore we can write formal series for our eigenfunction phi and eigenvalue omega in this form. So we substituted in the our equation, then trivial calculations gives us that the first term in this series phi 0 equals to 1, and the second term x1 equals to 0, and we have the terms for the omega 0 square, which is c0 p square. C0 is some sort of the average of the inverse of the c square of our initial coefficient, and omega 1 is 0. But it's not all what we wanted. We wanted the next non-trivial corrections in this series. And we can, after some calculations, we can present function phi 2 in this form, p square psi 2, where psi 2 is the solution of this problem, which we call the cell problem. And also, after some calculations, we found that the next non-trivial term, omega 2, has the form minus p4 c0 square, and here's the average of the gradient square of our solution of our cell problem. So this gives us this representation for our solution, approximate solution for our eigen problem for the phi and omega square. Here I wrote fourth power because I calculated more, and this next term is also 0. And for shorters, I denoted as psi av this average of the square of derivative. So now let's go back and talk about our function phi. We need to find the function v tilde also, because it's part of our solution. And v tilde is the exponential, and we can take the inverse Fourier transform, and we will obtain the solution. But I want to mention that this function v tilde satisfies this ordinary equation. Yes, so second derivative of v tilde equals omega square v tilde. So it's from this form of the exponential can be seen. And this means that the inverse Fourier transform function Vx satisfies this equation. Yes, and this equation has no any fast oscillation coefficients, and we call this equation the homogenized equation. And we pose the initial localized conditions for the function v. So this is our equation, and we want to discuss the solution of function v of x as the solution of the homogenized equation in this sense. So we can, as I said, we can take the Fourier transform. So we need to calculate two integrals, which corresponds to the two branches of the square root. And v tilde here is the Fourier transform of our initial localized conditions. And so the solution has the form of sum of two functions, v plus of xt and v minus of xt. And so here we want to analyze this solution. And for that, we want to approximately calculate these integrals for function by v plus minus. And this leads us to the asymptotic analysis of the presented solution. And I'm going to discuss the simplification of these integrals and to discuss some dispersions effects which appear here. So in order to analyze these integrals, let's use the Taylor formula for our frequency and present the square root of our frequency in this form. So C0 of P minus epsilon square mu square, P third, CF, and etc. And let us substitute it in this exponential which appears in the integral. And so let us suppose now that we have this relation between epsilon and mu. So as I recall, in real applications, epsilon and mu are fixed numbers. So they are maybe small, but they are fixed. So we need to adjust our asymptotics and these applications where they are not some they are small constants. So, and for example, in that case, you can see that when we here we have 1 over mu, and then when we divide epsilon square over mu third in mu third power, here there will be some small correction. And therefore, in this big exponential, we have only the linear term for which affects our solution. And all other terms are quite small, and mu is sufficiently small. But from the other point of view, if we suppose that we have this relation when epsilon square equals some sort of equals to the by order by third power of mu, then the correction in this integral in the frequency appears, which we need also to take into account because it's order of 1 becomes, yes. So in that case, we have this exponential, which gives, and this is the correction which we want to discuss. So let's talk about the absence of the dispersion effect. So if we have the linear dependence, we call it that this case is the absence of the dispersion effects. We can present asymptotic solution Vs as the approximately as the sum of these two integrals, which are just the Fourier inverse Fourier transform of the function V tilde, which gives us two waves. Yes, so solution of the wave equation with constant coefficients. Yeah, so this our asymptotics is the solution for wave equation with constant coefficients. And what means that the absence of the dispersion effect? That means that in time, our wave, localized wave, propagates and remains the same shape in time. But if in the second case, we have this correction, yes, when epsilon is order, epsilon square is order of mu third, then we call that the small, so we have nonlinear dependence of the frequency on variable p, and this means that we have the dispersion effects, and since this parameter is small, we call it the small dispersion effects. And consequently, two integrals are of the form with this correction. So if we choose initial function in the form of v tilde, in the form of Gaussian exponential, then we can calculate this integral in the form of the area functions. And the area functions are the solution of the of this ordinary differential equation. It has two solutions. One is bounded, AI, the other is unbounded, BI. So this BI, and blue one is AI. And the function AI has this very nice integral representation. And therefore, we can also calculate this integral for the asymptotic solution, v plus minus, with this third power correction in the frequency. And so here is the solution. It's an asymptotic solution with exact calculated integrals for the Gaussian exponential. And I'm sorry, and I substituted here epsilon equals to mu over 3 over 2 for simply some sort of simplification. So formulas are quite cumbersome, but again, it's analytical formula, which is very nice. And what means that we have this dispersion effects? It means that in time, our localized wave becomes, it is spreading in time. And also this leads to appearance of the some small oscillations of the main head wave in our after our head wave. So now what the equation will be for our asymptotics function Vs. And so we can recall that we have this omega square, and we have this correction here, and this this correction corresponds to the fourth derivatives for the, in our equation, and therefore we can say that the asymptotics satisfies to this equation with some correction which which has fourth derivatives. Okay, and so this is this is it. So what we want to do next is that we want to extrapolate this approach for the more complicated case with the more complicated form of the oscillations, and with some additional smooth background, depends on the smooth background. And also I want to take into account, so we go to the n dimensions. So, and as I said, this can be done with the help of the operator methods and adiabatic approximation in the operator form, or operator separations of variables, fast and slow variables. So the idea is still the same, but it's more complicated from technical points of view. So let's go to the general case. Now, let us recall the initial problem. So this is our initial Cauchy problem in n dimensions. So we have our oscillating coefficient c square of theta theta over epsilon and x. Again, we want to talk about the asymptotics when mu goes to 0. And in this situation, I will assume that we have this relation. So this means that this is the threshold when the threshold between two relation of two parameters when the dispersion effects appears, as we saw in the example. So again, the idea is the same. So we have the ansatz, which is the psi capital, where we separate the dependence on the fast variable, slow variable, and also this function depends on the small parameters. I will not write this dependence here, but we need to remember this. And a substitution of this function psi into our wave equation leads us to this leads us for the equation with this function psi. So I multiplied here by epsilon square in order to have epsilon in the upper parts of the fractions. So here epsilon square second derivative of time equals to h hat, which hat is the operator which acts on the function of psi, and h hat is this operator here. So c square of yx is our function of c square, which describes our coefficients. Epsilon nabla is the derivative with respect to the variable x, and theta y is the some sort of twisted gradient. It has this form. So nabla theta capital is this matrix of the gradient columns, theta 1, theta 1, theta m. And so we twist this gradient with respect to the variable y by this matrix. If theta of x equals to x, then this matrix gradient theta equals, it is identical matrix. So in that case, we have this nabla y, and the brackets here stands for the traditional Euclidean product of the vector. So this is vector, this is vector. So we have this product of inner product of the vectors in the traditional sense of divergence of div grad of this operator. So now we are looking for the solution psi, for the function psi, in the same form, not the same, but in the analogous form as we looked for the in the example. So we have function, not function, but operator phi, which now depends on the slow variable x, derivative operator with respect to x, and the fast variable y, which acts on the function v, which depends only on the slow variable x and time. And we assume that the function v satisfies some equation with smooth coefficients. So epsilon square second derivative of time equals operator L, which depends on x and derivative of with respect to x times acting on function v. So this derivative, this operator L, will be the analog of our operator, differential operator, which appears in the example when we have the frequency omega square. So this is our analog of this omega square, but now it depends also in the it is with variable coefficients. So, and the task here is to determine operator phi and L. So these operators also depend on epsilon and mu. I do not write this dependence. So we have a proposition, the following proposition. So suppose this function v satisfies this our equation. And suppose we have this operator equality between which connects all our operators. H, which appears in the equation for the function psi, phi, which is in the separation of variables, and L, which is operator in this homogenized equation with smooth coefficients. So, and if these two equations hold, then the function psi of our form of operator phi acting on function v will satisfy our initial condition, initial equation epsilon phi psi second derivative of time equals h psi. And similar to the our example, this operator equality h high equals high L, we can treat in the same way as the spectral problem with respect to the operator y, with respect to the fast of variable y with periodicity conditions in the torus 0 to pi in the power n. And again, we can find several terms of our expansion with respect to the small parameter epsilon over mu for the operators phi and L. So let us define the following function. So here again, we have our this special averaging of our initial coefficient c square, 1 over c square, with respect to the variable y. Now it depends on the small parameter, slow variable x, because our initial function depends on the smooth background. And we also want to define the function psi2, again, the solution of the cell problem, but it is, again, will now depend on the slow background x. So minus delta y theta psi2 equals c square small minus c square capital over c square capital with zero mean condition. So delta theta y, it is again Laplacian. Yeah, so it is some sort of, again, twisted Laplacian. So we have this twisted gradient times twisted gradient as the as the scalar product of the operators. So, and then we can formulate the following theorem. So the problem with the smooth coefficients has the following form. So second derivative in time equals c square p square hat p square. It is our gradient. So p square is our Laplacian with multiplication of mu square. So our Laplacian acting on v plus c square of x. The average of the gradient with respect to y modulo square of our solution of the twisted solution of the cell problem. P hat 4 is the fourth derivatives plus some correction. So operator L contains derivatives of the higher order with respect to the fourth derivative of this term. And the symbol L of xp is a smooth, fine, very nice function. And we want to define function asymptotic function Vs, which is satisfy this homogenized problem with residue of mu square, of order mu square. And we call it this principal term of our asymptotic solution of our initial problem. And if epsilon equals to this order of mu, then this correction does not play a role, and we get the correction for the fourth derivatives. So this next statement, and if we have asymptotic principal term of our asymptotic solution of the homogenized equation with this relation between parameters, then we can construct the function u, which gives us the solution of our initial wave problem. Here I multiplied it by mu square because, again, we have this localized conditions. So the traditional derivative is order of 1 over mu. So in order to have this derivatives of order of 1, I need to multiply it by mu square. So, and this asymptotic solution has the form. So operator high of this form, so 1 plus some correction with the solution of the cell problem acting with the second derivative, plus these two operators, which can be calculated after some solution of the ODEs, and acting on this principal term. And as you can see, this 1 plus some small corrections, and that's why we call this Vs as the principal term of our asymptotic solution. So let's do the summary. So we have the following homogenized problem, the smooth coefficients. The asymptotics is constructed by means of semi-classical analysis. If we have this relation, we need to take into account only this part, and this is the wave equation for the asymptotic solution. And this is the same situation as in traditional homogenized problem, where we have only this principal term for our asymptotics. And in this case, because we have the special form of the non-divergent form of the equation, we don't need to determine we don't need to solve the cell problem. So yes, the cell solution of the cell problem appears only in the correction when we have this relation between our small parameters and when the dispersion effects appears. And so in this case, we need to solve the cell problem, find solution, find function psi2, and this is will be the correction for the asymptotic solution for our principal term. So we have the equation with fourth derivative. So this is all. Thank you for your attention. Muito obrigado. Thank you very much. Thank you.
Okay, thank you very much, Sergey, for your nice talk. So let's ask the audience if they have any questions or comments. So you can use your microphone. You can speak, and also you can ask by chat. So are there any questions? Yes, Juan is telling that the video and audio are open, so please go ahead. So while people thinking, just some curiosity, and what about if you consider your problem in a bounded domain? So what about if X is in the bounded domain of Iran?
There is a question of how the solution and coefficient behave near the boundary. It will be much more complicated because we need to take into account the reflection from the boundary, and this is quite different situation. I didn't think about it. So it's different kind of problem. I think something can be done in this general approach, but it is more complicated. So you need to take into account the boundary condition, which also will affect the ansatz of the solution. And here we just have the localization, and so it's 0 on the infinity, some sort of 0 boundary condition outside of some ball. But if we have the bounded domain, it will be more complicated. So we need to adjust this approach. But yes, and it has some difficulties, technical difficulties also. Yes.
Okay, thank you. So I think Evelina, please go ahead.
So I have two questions. On slide 16, you showed the series, it's a Taylor series. You said it's formal. Okay, so if it's formal, can it not be a Taylor formula?
I don't no.
So what do you mean by a formal Taylor series?
It's formal. It's formal asymptotic series. So when you have
can't you use the Taylor formula instead, which will be like a formula?
I think this is the main part. This is the main difficulty here, that if you use the Taylor formula, you have some sort of the finite sum and this correction. You need to give the estimate for your correction, and using the formal series, formal power series, means that if you take the cutoff of this series, then the correction is of order of the epsilon over mu and this some power. So this is it. If you use the Taylor formula, you need to give the estimate for the correction in this formula. Yes, this is the question, and This is very technical and complicated question.
What do you mean by formal? You just cut it and say that this is your the function that you're going to use?
No, Taylor formula.
Formal series. Why you use the word formal?
No, because there may be a situation we don't
Not converging.
We don't discuss the convergence of these series because in some cases it may not be convergent, I think. So there are several situations where it cannot be convergent.
That's why you would better use a Taylor formula, no?
But for Taylor formula, you need to estimate the you have the finite sum and the final element in the Taylor formula is some sort of the correction, this you need to give the estimate for the correction.
Okay. Okay, maybe not completely clear, but okay. And the other question is when you talk about your asymptotic solution, you give some definition, which is when the difference from the original equation is big O of
this one.
But then your term is your correction term, is it not epsilon squared to me squared?
I don't understand.
So
you mean
okay, but as I remember, then you show something and then say something. Okay, this is my correction term.
So this is it.
Not of this form. It's not of this form.
No, I don't. Where? When? Here? I don't understand the question.
Do you not have an equation for this VAS? And then you show in red as something, and then you say that this is a correction form.
This one.
Okay, this is a one-dimensional case.
Yes.
But in one-dimensional case, it's epsilon squared something. So it's a different definition of an asymptotic solution.
It's you see here. I also need to multiply it by mu square. So if you, for simplicity here, I'm sorry. Maybe I didn't do that. I shouldn't do that. I didn't multiply this equation for the mu square, but if I multiply it by mu square, here I have mu square. Here I have mu square second derivative, and here I have mu fourth derivative over mu square, mu fourth over mu square, and here we appear this epsilon square over mu square. So you need to multiply it in order to obtain.
And epsilon over mu is smaller than 1.
Epsilon square over mu square. Yes, it's small.
Okay, thank you.
Okay, thank you very much. Are there other questions? So if not, we thank you, thank the speaker again, and
Thank you very much.
Okay, yeah, you can stop for recording.
Thank you, Anna. Thank you a lot, Professor Sergey Sergeev, for your amazing talk.